Welcome to the Polones project, Effective One-Electron Potential Operators for Computational Chemistry of Extended Molecular Systems. This short video explains the OEP procedure, which was designed to facilitate the implementation of fragment-based methods for modeling condensed phases. Computational chemistry is a field of constant, intensive development. However, with rapid advance of technology and medicine, it faces new challenges. This ever-growing demands field requires studying increasingly larger and complex molecular systems. To make it even more challenging, it has to be within a reasonable computational cost and accuracy. Among many techniques widely used nowadays, fragmentation methods offer robust and systematic approaches to model complex molecular systems, such as liquids, crystals, proteins, nucleic acids, and many more. In many of these methods, so-called electron repulsion integrals are the bottleneck of calculation. They typically also require large memory allocation. The aim of this project is to design a general, simple method to eliminate those electron repulsion integrals from the fragmentation methods. This should significantly lower computational demands. The proposed method, called the OEP procedure, consists of three major steps. In the first step, the parent theory is chosen as a starting fragmentation method involving electron repulsion integrals and other costly mathematical operations. In the second step, mathematical formulae of the parent theory are grouped into three subgroups, each containing different type of electron repulsion integrals. This involves three centers associated with the same fragment, we call them overlap-like integrals, and two same centers, we call them here Coulomb-like or exchange-like integrals. In the third step, OEP procedures are applied separately on each of these groups of formulae. This is done to effectively eliminate electron repulsion integrals. In effect, it generates expressions which are much cheaper to be evaluated. The OEP procedure is based on this definition of the effective one-electron operator. Various functionals of electron repulsion integrals, denoted here in red, as well as one-electron operators, are summed all together. This encapsulates them into a single one-electron effective potential matrix element, shown in green. Such a design is inherently linked with the concept of the effective potential, which in principle offers great possibilities of reducing computational costs in accordance to the fragment-based methodology. Let's see how three different types of electron repulsion integrals are treated in this project. The first type is the least approximate way to represent through one-electron potentials, that is, the overlap-like electron repulsion integrals. Conventional density-fitting method can be used to convert these electron repulsion integrals into an inexpensive contractions of constant matrices and one-electron overlap integrals. This comes with virtually no loss of accuracy. In this project, the density-fitting method has also been extended to use auxiliary atomic orbital basis sets that are much smaller in size than the primary basis sets. This reduces the cost even further as compared to the standard density-fitting method. The second type is the Coulomb-like electron repulsion integrals, which resemble to some extent semi-classical interactions between effective charge density distributions. Therefore, they are treated through the distributed multiple expansion, where relatively inexpensive tensor contractions between multiple moments are denoted here as the circle dot symbol. In this project, the local overlap approximation has been also introduced, which assumes localized occupied orbitals and also zero overlap between different orbitals. This approximation further reduced the computational cost, but is also more approximate than the distributed multiple expansion approach. The third type is the exchange-like electron repulsion integrals. Although in principle they cannot be represented by any one-electron potential, they still can be approximated as a sum of the products of Coulomb-like electron repulsion integrals and the overlap integrals. For example, by using the Mulliken approximation, it allows further application of techniques similarly as discussed for Coulomb-like integrals. This technique is the most approximate out of all the OEP procedures. Let's look at some examples illustrating the use of those three distinct OEP procedures. This expression is used to calculate the charge transfer energy between two molecules. Originally, it will require to compute matrix elements of the nuclear attraction one-electron operator, as well as a collection of overlap-like electron repulsion integrals, shown in red. This relatively costly operation, mainly due to the electron repulsion integrals, can be greatly simplified by using the OEP procedure. By using the extended density fitting method, a very inexpensive contraction of a constant matrix G and one-electron overlap integrals, shown in green, are produced. Another example in the same charge transfer energy model involves nuclear attraction operator and Coulomb-like electron repulsion integrals. By applying the local overlap approximation, we can drastically reduce the cost, where all electron repulsion integrals and summations were effectively removed. As a result, the computational cost of the term shown in green is negligible. This is because it involves only localized molecular orbital charged centroids and atomic centers. As opposed to the previous example, local overlap approximation is more drastic treatment than the extended density fitting. In this last example, two forms of exchange-like electron repulsion integrals, involving HOMO and LUMO orbitals on either fragment, are used in excitonic energy transfer coupling evaluation. Application of the distributed multiple expansion and local overlap approximation results in a cheaper term shown in green. The only time-consuming steps are the products of overlap integrals, which are relatively inexpensive and require very little memory. To summarize, we generalize the definition of the effective one-electron potential operator for the use in fragment-based methods of computational chemistry. By doing so, three distinct classes of electron repulsion integrals were defined and treated with the newly developed extended density fitting method and some well-known approximations. These OEP procedures, once applied to the fragment-based models involving electron repulsion integrals, allow to reduce computational costs, both in terms of memory and computational times required. To learn more about our project, see these open access articles. The project has been funded by the National Science Center in Poland and the European Union Horizon 2020 program. Please check out our other videos for more details, including applications of OEP procedures of a couple of computational chemistry problems. Thank you for watching.